So we are going to continue with chapter 3 of Onishchik's book. Basically, last session we wanted to prove the following: that there's a one-to-one correspondence between classes of real structures on G, where G is a real semisimple algebra. Sorry, complex semisimple algebra. And classes of evolutions. So real structures are just like an involution, but they are antilinear. They're often called anti-evolutions. And we want to see that we can convert this into a linear thing in some sense, and it won't change the outcome of the correspondence between real structures real forms and the involutions. Well, these classes are both either by conjugacy by inner automorphism or by conjugacy. And the other day we started this by proving that there exists, this is a bit of a spoiler, maybe, unique amplitude conjugation. Let's see if we manage to prove this today. Compact wave structure, which we call tau on G. And today we will try to prove the following. First of these is that this correspondence looks like 6. This correspondence, which takes sigma to sigma tau, takes real structures commuting with tau into evolutions. And the second thing is that as we will require our real structures to commute with this tau, we are going to work on congruence classes. So we are going to try to prove, if there's enough time, that for any real structure, sigma, there exists an inner automorphism of G such that by conjugating with this inner automorphism, the conjugation of sigma with this automorphism commutes with that. So we are going to start with this thing right here. Say that there always exists a compact real structure, which is the only one that we know the sure existence of. So we are going to fix it from now on, and we will consider this map which is obviously linear. And as this will be unique in some sense, it will make sense to do this. So we're going to consider the map. It takes a real structure, takes it into a automorphism group of G, which takes sigma to sigma. Of course, this is an automorphism because both sigma and tau preserve brackets, and since both sigma and tau were antilinear, their composition is linear. And we say, we're going to note this by theta. We say that the automorphism theta corresponds to the real structure. Of course, this must be injective because if you take tau on the other side, you get back sigma, right? Not all of the automorphisms appear of this form, but of course we can have two real structures when considering automorphism. In particular, the identity corresponds to taking sigma equals tau. Right? And now we have a proposition which is the following. We have three facts about this correspondence. The first of them is that this correspondence is a projection between the set of all real structures in G, and we set the automorphisms of G such that tau theta tau is theta minus 1. Second of these properties is that theta is an involution if and only if sigma tau equals tau sigma, and the last of this is that if we denote sigma the automorphism corresponding, sorry, theta the automorphism corresponding to sigma, and alpha an inner automorphism of G, the automorphism corresponding to the conjugation of sigma by this inner automorphism is not the conjugation of this theta, but is something similar. It's alpha theta, tau alpha, tau minus 1. So we compose from this side with alpha, and here instead of taking alpha minus 1, we have to conjugate the alpha with tau. Right? So I'm going to give a quick proof of this. So the first of this is just because tau sigma tau, tau sigma tau. This is tau sigma tau squared, which is the identity, sigma tau. This is tau sigma squared, which is the identity tau. So this is tau squared, which is the identity. So this is tau, theta tau, and this is tau. So as they are both isomorphisms, real isomorphisms, this has to be the other way around, has to be true as well. And conversely, if we have given an automorphism given such that theta to the minus 1 is tau theta tau, the corresponding real form is sigma tau. One can quickly check that this map is an inverse to the Doppler map because tau squared is identity. And now we have that theta tau is antilinear because tau is antilinear and theta is an automorphism, so it's linear. And theta tau squared, theta tau, which this is theta to the minus 1. So this is identity, right? So this gives a rejection. Also, it's easy to see from here that if we define theta this way, sigma tau equals identity, theta only multiplied by both sides for tau sigma, sigma tau sigma equals tau sigma. And now this is identity, and we have sigma tau sigma squared equals tau sigma, and this is identity again because they were both anti-involutions, right? And so yeah, we have item number 2, and the third item is also really easy. You just have to write what's the automorphism corresponding to alpha sigma alpha minus 1, and this is alpha sigma alpha minus 1 tau. But then you can put here tau squared because tau squared is identity. So this is just alpha sigma tau squared alpha minus 1 tau. And this is alpha pi tau alpha minus 1 tau, which is the same as alpha pi tau alpha tau. because tau is O inverse. So yeah, we have basically that, right? We have this correspondence gives us evolutions, which is what we want, precisely when the maps commute with each other, right? So when our real form commutes with the compact real form that we have fixed. Well, as we want to have always evolutions, that's why we pass to conjugacy classes. We have to show these things. The following thing is that for every real structure, we are going to have an element in its conjugacy class, which will commute with this tau. To avoid having to repeat this every time, we will just introduce here some notation. It's a serial form of real structures. Are compatible if the corresponding real structures commute. And if we are working already with the real structures, we see that they are compatible if they commute. Right. So, the aim now is to construct the correspondence between classes of real structures and classes of evolutions as follows. We take the class of a real structure sigma. We choose a conjugacy class, right? Yeah, conjugacy class of sigma. We take an element in this conjugacy class, sigma prime, commuting with tau. We send it to sigma prime tau, and we take its conjugacy class. Okay. Of course, this is an evolution because sigma commutes is compatible with tau. So we now have 3 points to show. The first of them will be the work of today because it will be the long part, and hopefully we can study it until the next following day. Which is the first of them is every real structure is conjugate to a real structure commuting this is which will allow us to define this one precisely. Then we have this is what we have. And this is a projection. And then I mentioned that this tau is going to be unique up to conjugacy. So we want to see that this does not depend on the choice of tau. we are going to start with item number 1 today. And for this, we will need to talk about self-adjoint endomorphisms, positively definite endomorphisms, and exponentials. So, okay, so B is going to be an n-dimensional vector space. Over C, equipped with a symmetric Hermitian in the case of very complex vector spaces by linear. Which I will note like this. And alpha is going to be an endomorphism of B. I score that's a blackboard. The adjoint endomorphism to alpha, which we denote by alpha star, is the only endomorphism satisfied. That alpha xy is equal to x alpha star of y for x and y. So yeah, this is basically linear algebra, right? And alpha is self-adjoint if alpha is equal to its adjoint variable. Equivalently, alpha diagonalizes with real eigenvalues. Okay, so this is it. And we will denote by S of V the space of self-adjoint. And this is a subset of the endomorphisms of V. Also, we say that an endomorphism which is self-adjoint is positive definite if taking the inner product of alpha vector and other vector is a positive definite eigenvalue. So, yeah, if taking alpha of something finds a positive definite, either Euclidean product or Hermitian product, we denote by P of B, this is a positive definite self-actualized operator. Well, okay. And this is a subset of, so this is equivalent to diagonalizing with positive eigenvalues. So as this has positive eigenvalues when diagonalized, it is invariant. Because none of them can be zero. So we have something like this. I'm not going to write this for the moment because it won't be a early exponential, because either this is a subgroup and this is not a vector space, and that's algebra. It in some sense the exponential of this behaves well with these equations, right? So we have the following proposition. Maybe I should also split this blackboard. If X is a eigenvector for the alpha as a self-adjoint operator, X for lambda I for lambda. X is an eigenvector for the exponential of alpha for e to the lambda. This is just because of the properties of the matrix exponential, right? Thus, we have that exponential map when restricted to S of B. This is indeed a bijection, and if we take the basis for a given automorphism, basis of eigenvectors for given endomorphism alpha, which, as it is a self-adjoint operation, we know that if the diagonalizes in a basis of eigenvectors, we can take this. To this is the same basis. And if we take an endomorphism here, which is positive definite, we can take a basis of eigenvectors and define its inverse, which will be a self-adjoint operator, like just taking it to the endomorphism, which is the logarithm of the eigenvalues with respect to this basis. We'll be comparing basis of eigenvectors. And respectively. Okay, so for ease of notation, as this defines an injection, we note log P of E to S of E to be just the inverse of the exponential restricted to S of E. Okay. So we know this defines a bijection, but in principle, it is only a bijection between sets. Doesn't have to behave well with multiplication as the exponential does. So we have this other proposition which says that it does behave well. So given alpha a positive definite self-adjoint endomorphism, there exists a unique one parameter subgroup per the generally linear group will be such that alpha p is a positive definite endomorphism for all p, and very good. A of p. That's an alpha. Yeah, alpha. Okay. Sorry, this is not alpha. This should be beta. Oh, right. Because alpha is the beginning. So beta 1 will be alpha or something like that. Yeah, beta 1 is alpha. So it's basically just like taking the Lie group exponential, right? But you can't you can say is the exponential map of P of B, because P of B is not a subgroup. And how do you do that? So, well, it has two properties, two extra properties. It is that it's a distance, and these two properties are for free. Satisfies that its derivative at 0, it's log alpha, so which will be the tangent vector, which is in S of t. And if t is a natural number, sorry, what is t? No, oh, sorry. Ah, okay. Okay. Yeah. If t is a natural number, then alpha to t. So the exponential composing just alpha t times, right? And what's the proof of that? Well, first, if this was truly a group exponential, this will be its derivative. So the integral curve, this one parameter group will be obvious like this. Will be our main candidate to beta, which is the exponential of t times log alpha. This is a vector, automorphism, which is self-adjoint by definition. So this is in GL in Gothic letters. This will also be there because it's a algebra. We can consider its exponential as this is something matrix with real eigenvalues, and this is a real number. T times this is a matrix with real eigenvalues, so it's self-adjoint also. And take it exponential will lay again on P. Right? Okay. Also, beta 1, the exponential, the logarithm of alpha, which is alpha by the previous proposition, and beta prime 0, it's log alpha by the properties of the exponential. Yes, right? Mm-hmm. Okay, so such one parameter subgroup exists. Now we just have to prove that it is unique. Also, of course, has to satisfy this and this, right? This is this, and this is because it's one parameter. And now we have to prove that it is unique. I think this wasn't done in Onishchik's book, but it's not difficult to prove. Suppose beta tilde is another such parameter subgroup. Then we have the following. Beta tilde of n is beta tilde of 1 plus 1 plus 1. This is a one parameter subgroup, so this is the same as beta of 1 beta of 1 tilde, beta of 1 tilde, which this is just alpha to the nth power. So this also proves the other claim, proposition, right? The last one. Also, of course, beta also satisfies this, because we're only supposing that it is a one parameter satisfying that. Also, beta of 1 over 2 to the cube to the power of 2 to the cube. This is beta of 1, which is alpha. And alpha is a positive definite bilinear form now. A positive definite self-adjoint operator, so we can compute its square root and its fourth root and so on. So we have that beta of 1 over 2 to the cube. It's alpha to the power of 1 over 2 to the cube. This is just a root of a positive definite matrix. So, in particular, we have that beta of n over 2 to the cube has to be alpha to the power of n over 2 to the cube. So, the values of beta tilde are fixed in the rationals of the form n over 2 to the cube with n and q natural numbers, right? But this, which are dense. In R. So we know that beta satisfies this if we have another one parameter subgroup satisfying this. They coincide in a dense subset of R. They are both continuous and they are differentiable, so they have to agree in the whole of R. Also, from this, we have another stronger thing. I didn't say it before. Which says that if x is an value the vector for alpha with a eigenvalue and x is an eigenvector for beta T with any other lambda to the power for a real number. This is just because of you know what the eigenvalues of these things are, and this is dense in R. So we have to have this, right? For simplicity, we will write beta of t equals alpha to the power of t for a real number, right? Okay. And I would like to make a remark, which is that I will say this as a type because I won't prove it. In the complex case, the previous stuff for multilinear to have inverses. Okay. So now, as I guess you suppose, we want to substitute this V, which in principle it was arbitrary, for our the algebra and see how things work.
Sorry, but what do you mean by the same follows for?
That I guess you can define the notion of positivity and self-adjoint operators for an antilinear map vertical operator.
Mm-hmm.
Maybe by taking conjugate in the scalars. And then you have that there will be a correspondence by taking exponentials between or taking just the group exponential of GL. Yeah. Well, the corresponding. Instead of taking GL, you take the, I guess, here the maps from G bar to B.
From zero to.
Somehow we pass to the context of I will think about it so and let you know in the next session. But
So this was done in the real case.
no, in the complex, real complex case, but for linear maps, not antilinear maps.
Ah, okay. Now I understand. Okay. Yeah. Yeah, then.
Yeah, I guess you can just, instead of taking here GL of B, maybe you have to take something like that. I'm not sure.
Yeah.
Maybe I will try to do it more carefully, or maybe just might modify the notions of
Now I don't see why.
of positivity.
But I think in practice what happens is that when you're taking into linear maps, since the inner product is going to be skew linear in one variable and linear in the other one, I think in practice the only thing you're doing
Oh yeah,
replacing the variables. That's what you're doing. So this is everything should hold true.
but you are conjugating the variables, but you are going to have real eigenvalues. Yeah. So this probably works, and you will have to modify
Yeah, you
it.
will have conjugate.
Okay, so for example, if alpha is anti-linear and x is an eigenvector for well, what is an eigenvector for an anti-linear map?
But you have to look at the real case. You have to look at the realification. Yes.
I'm not sure. Think is, I guess, it's an eigenvector of a real map, of an anti-linear map, the eigenvector of the corresponding linear map, or the conjugate.
No, but you introduce a minus sign somewhere. So imagine that you have a complex linear map with eigenvalues alpha 1 to alpha n. Okay? And these are real eigenvalues. Then when you consider this map as a map for real spaces, consider this map defined the verification, so it's a real map, then which eigenvalues do you have? The same ones, right?
Yeah, and they appear repeated, right?
Yeah, and they will appear with multiplicity twice. Yeah, okay. Very linear. But now, if this is not linear and it's anti-linear, you will have minus signs.
Yeah, I guess what you will have is something like.
Yeah, you will have one minus sign more. Yeah.
But
And this is dangerous because you don't have longer, you don't have a positive definite.
But what you can do is you take the bilinear form induced by the antilinear map, and instead of putting it in the linear slot, like you do with the linear maps, you put it in the skew linear slot, so the skew linearity of the bilinear form cancels out with the skew linearity with the antilinear map. So maybe that's why everything.
Yeah.
but that should be the same because we are going to work with self-adjoint operators, right? So I guess think of defining the self-adjoint operators for an antilinear map is going to be the same stuff.
Yeah.
This equals this, which makes
Perfect, inner product.
Yeah. Is that okay? This takes out this takes out scalars on the first part with a bar.
Yeah.
So I guess you just say that the second part. Just say that this is going to be positive definite if the fifth Well, I'm going to call it the sum up. The associated bilinear form. The sum up of it. Yeah. It's a definite positive product. I guess this could work. I don't know, I have to check. I'm not sure at all. I didn't look into it. Is Hermitian because of the inner product. It takes scalars out.
No, but depending, now it's not Hermitian anymore.
Okay.
You have to put it on the other. No, but if you put it on the other, it's not Hermitian anymore. It's, no. This is not going to be Hermitian.
So.
No, but it's the same problem. Since it's antilinear, you will always take the scalars out with a bar. Independently of the entry.
No, here.
This one, yes, right? So you are
No,
taking
here you take scalars without the bar.
but in the other as well, because alpha is antilinear.
Yeah. Let's have to take a look. Yeah. Well, anyway, passing to the algebras. I mean, the other propositions have to work because we only use the sum of that.
No, you use real sums and the compositions, and that doesn't depend on the real or complex. As long as you don't use scalar multiplication, you're fine.
Yeah. I mean, what you have to guarantee is that it is positive definite if only if it has positive eigenvalues, right?
Yeah.
And self-adjoint if and only if it has real eigenvalues. Once you guarantee that with your definition of self-adjoint and positive definite, the rest will work because it didn't use the fact that it was linear.
Yes. Yeah. And you think that here in the chapter, he's never considering a power of an antilinear, no? So maybe it's not that really important remark.
Oh, sorry. Yeah, I forgot about one thing previous to passing to the algebras. That if let alpha be a positive linear, positive self-adjoint automorphisms, and gamma element of GLD, and let beta be. So what happens when you conjugate, right? First of this is that the logarithm of beta is just conjugating the logarithm of alpha by gamma. And this is immediate because the logarithm, we define it in the terms of choosing a orthonormal basis and taking the matrix with that orthonormal basis and eigenvalues, the logarithms of alpha, and change correlation just corresponds to a change of basis, right? And the second one, beta to the power of t, is gamma alpha to the power of t, gamma minus 1. So this must be the one that was true. Maybe. Nevertheless, you have to find an equation of positivity in that particular case, right? So why is this? This is because beta of t is the exponential of t times gamma logarithm of alpha gamma minus 1. But this is the exponential of t times the joint representation of sigma. So where this adjoint, we are taking it in the adjoint representation of G of B. It's the other one, right? But now this is linear, so this is 1 alpha. That the joint representation is the derivative of conjugation by sigma, because we are working on matrices, so conjugation and that joint representation are the same. So this goes out as the conjugation by sigma of the exponential of t times 1 alpha. And this is just sigma t times 1 alpha. And okay, and this will be important later on. Because we are going to calculate like this. Okay, so now we do fast to the algebras. We have the following lemma that G is a complex or real algebra of finite dimension with an inner product which or scalar. Which we will denote by this. Theta will be an automorphism which is positive definite with respect to this inner product, right? This is so we can exponentiate it. Then sigma to the power of t is an automorphism for t. And if G is semi-simple, then it is not only an automorphism, but always a linear automorphism. And why is this? Because let us write G as the sum of its eigenspaces. For theta. And let X be an eigenvector for some lambda I. And Y be an eigenvector for some lambda J. Then theta of the bracket of S with I, theta X, theta I, because this is an automorphism, and this is lambda J, lambda I times the bracket of X and Y. So the bracket of X and Y is an eigenvector with eigenvalue lambda I times lambda J. So by the properties that we explained before, sigma to the power of t of the bracket of X with I is for t.
Sorry, but the bracket of X with Y could be 0, right? And then there you go.
Yeah, nevertheless.
Okay, but you are not claiming that.
Yeah, I'm not claiming that that is a non-empty eigenspace, sorry.
Okay.
Just that, yeah, the bracket is that.
Yeah. So what I was saying is that you're not claiming that the same property that holds with root spaces, that the bracket in two root spaces is.
Yeah.
This is not holding here.
That is not hold, well, it's holding there in a generalized sense, right?
Yeah.
If you consider
Yeah. Well, it's similar.
the root space to be zero.
It's similar. Yeah. It's similar.
Yeah. Okay. But that is an independently 0 is an eigenvector for any eigenvalue. But this is lambda I, lambda j to the power of t xy, which is the same. This is lambda I to the power of t x, lambda j to the power of t times y. These are real numbers. I have no problem here, but we know that this is I to the power of tx, I to the power of t y. So e to the 10 is an automatism. we just use the properties of root spaces and the properties of this exponential to put that as we can find the basis of eigenvectors. We pass the basis of eigenvectors. We work with real numbers, which we know we can put inside our brackets however we want. So this must hold, right? The last assertion follows because phi to the power of t is the exponential of something, and if g is semi-simple, the interior automorphisms of G is the connected component of the automorphisms of G, which I think was part of the first session of the model 3 months ago. However, it shows up now. So yeah, if you are taking the exponential of something, it lies in the connected component, right? This must be okay. So
this is very interesting because now if you have an automorphism and you know it, you can, if you are able to compute its eigenvalues and you check that they are positive, you know that is an inverse.
Yeah.
Yeah.
Well,
So it also has to be
not really. Not
symmetric.
Not
Yeah.
really.
It has to be also symmetric. Yes.
If you have to check that.
Well, that it belongs to PEG.
That it is an exponential is I have to check that.
No, but I am talking about always in the semi-simple case.
In the semi-simple case?
Yeah,
so
yeah.
Sorry.
Yeah, what I'm saying is that if you have an automorphism in a semi-simple the algebra which lies in PEG, a set of positive definite operators, then it's interior automorphism.
In particular, because it's itself to the power of 1, right?
Yeah, because you make t equal 1.
Yeah, you make t equals 1.
Yeah, this could be useful sometimes.
Because, I mean, you don't have to check it here. It's the exponential of its logarithm. So,
yeah.
So that always lies. Okay. So I guess we're going to try to do this. Let's see if there's enough time. And this is another lemma. Probably next session there will be another 2 or 3. Maybe 2. Which says the following. For any real structure, sigma theta equals sigma tau. It's a self-adjoint morphism. Thus, theta squared it's a positive definite automorphism. Which in terms means that theta squared itself must be even, right? Say before. And for any evolution, psi is theta tau squared, so the corresponding real part squared. Okay, so this is any evolution of this. This might need not be a real part, right? It's a real form if theta and tau compute not the case. Okay, so how we do this? Number one, this is because theta of x comma y equals minus, well, here as the inner product, sorry, I forgot to tell, we are going to fix tau, and the inner product is going to be h tau, which, if I remember correctly, was minus the Killian form of theta comma tau or something. This was one we used to prove that the compact real form was in fact compact. Which was in a product because tau is a compact real. This is sigma tau x tau y. Now this is minus b of.
Why there is this tau?
On the second one?
No, the first one.
Because theta is.
Because of the relation. Okay, yeah. Sorry.
Yeah. So this is minus the Killian form of sigma tau minus 1 tau y. That's because this is an automorphism. And this is sigma tau minus 1. You should remember from proposition number 1. This is minus e of x tau theta tau and this tau squared. So we take that out, and this is h tau squared of x theta by definition of the inner product. So this is x theta. Clearly, if theta is self-adjoint, its square is it's positive definite, because we know that this can't have zero eigenvalues, because these and these are isomorphisms in the vector spaces. If we take this as a vector space, and thus we can have a zero eigenvector. So either we have negatives, eigenvectors, or positive, and we square them, they all will be positive. Real. And once we have this, assuming this thing theta tau squared makes sense because it's anti-linear thing. When we denote it by automorphism there, it doesn't mean that it's linear, right? Well, squared it is, yeah. When we square it is linear. So, yeah, never mind. Sin x times y. This is minus beta, minus b, sorry. Sin of x tau y, and this is minus b of x sin minus 1 tau y. Because this is an automorphism, because we're squaring it. So if it is anti-linear once, it is linear twice. And now we do the following. We write sin minus 1, and this is minus b of x, comma, tau, theta, tau, theta, tau, right? By definition of this. Because theta is an involution, so its inverse is just the inverse of theta tau, theta tau, tau, theta tau. So now we have following. This is the same as taking minus b of, this is sine again. We have sine here and then tau, but you put it like that and take tau first and sine second. So what thing is that basically? Sine minus 1, tau is tau sine. So this is minus b of x tau sine 1, and this is x sine. So sine self-adjoint, and now we have to see that it is positive, right? But sine of x is minus b of theta tau x tau x. But this is minus b multiplied by tau theta on both sides of theta tau x tau theta tau x. And this is the inner product of theta tau of x with theta tau of x. And check this out at your three. And then you just have the expression of the inner product, right? Zero. Okay, so take here.
But you have at the end tau theta in the second component, not theta tau.
Oh, yeah, maybe I was. No.
Why?
Okay, so multiply this by theta.
Yeah.
You have.
No, I agree with that, but just in the last line.
Okay.
Yeah.
Multiply this by theta. And now you have minus b of tau theta tau
X.
of x
Theta tau.
theta tau of x.
Okay.
Multiply by tau
Okay.
minus b
Theta tau.
of theta tau of x is tau
Theta tau.
theta tau of x.
Okay.
But this is theta tau of x times theta
Ah, yeah. For sure. Right. No, yeah.
because of the
Yeah.
And this is an inner product. These are
Yeah.
isomorphisms, modular vector spaces. So this is positive.
Yeah.
So we are going to finish with that because I think the next things, the next thing is a little bit more complicated. So that's when we are going to